to the processing line, that is we call online reprocessing process. So OLR, that's called online reprocessing process. Online reprocessing process we using frequently for large company is called inside, outside, birds wash. IOBW. It is very important, several things you need to be careful. Number one, the pressure. The nozzle has to work very well. It's a good distance, the pressure, and it's covered the big surface. So you can see the nozzle here looks good. Here not looking good. Some of the distance coverage is not enough pressure. Look at here, this doesn't even work. So need a certain distance, pressure, at the covered area. Now, during this processing, most of the time in the United States, people are using is coring. So we need to talk about this coring a little bit. So what is coring? You learned in your chemistry class. Let me just tear these off. I want to talk about coring relatively in detail. Because this is a big topic and lots of people have a misconception about that. So what is coring? It's you buy a bucket of Corax from the Kroger or from Walmart. Then you dissolve in the water. But can we just use it? Yes, you can, but I tell you the antimicrobial efficacy is not that good. So this is the reaction what's happening. This is coring with water. Then will be happen is and HCl. This is a reaction. The key here is actually this guy. This is called hypochlorous acid. This is hypochloric acid. Hypochlorous acid is, we say, free available chlorine. This target here, the concentration, is 40 to 50 parts per million ppm. But I tell you one thing, not only this. This hypochloric acid could be further reacted to become chlorine ions, and you release proton. So this gives you a trick. If in acid environments, what will happen? This reaction goes this way. Go the left way. Right, go the left way. This will be generated. And this acid concentration you have to control is usually weak acid environments. pH around 6.8. Now, I just to give you an example. The bucket what you buy from Walmart or Kroger, the Corax, you directly dissolve in the water. At that moment, the pH is high. It's about 12 or even 13. It depends how many you do. What happened is, this hydroxide will react with this acid here. Therefore, the reaction will go this way. They will dominate with this guy. This is chloride ions. We really like it because there is no strong antimicrobial activity. So, what's the key? Control the pH. Has to be around 6.5, 6.8. But some people are going to say, can we just keep adding acid? No, you cannot do it. If you keep adding acid, what happens? This kind of reaction go here. This will be more generated, become what? Off gas. If you are doing pH 3 and 4, the off gas is generated. This is some of the misconception also happen in the plants. So you know the chlorine will be reacted with organic matter. Organics, for example. Okay, they could bring down 50 ppm to 0 in like even 30 seconds. So what they do, they try to keep this 50 parts per million. They'll keep adding chlorine. When you keep adding chlorine, what happens? You generate lots of off gas because your weight is going that way. So generate lots of off gas. What is the feeling for you, the off gas? You're going to be tearing. Not really crying, but you're tearing in the plants. I was there a couple of times. Your eyes cannot even survive. That's what happens. So the pH control is very important. This is a curve, what I want to always introduce the person to talk about this. This is a curve, okay? The curve we usually draw like this. This is go 0 to 100, which is the hypochlorous gases. The x-axis is the pH value, so we usually do a 6 right here, 7 right here, 8, 9, 10, 11, 12. And what about here? This goes this way, 0 to 100. This is chlorine ions, which is hypochlorite ions. The curve looks like this guy. At the pH 6 or 7, majority of these are hypochlorous gases. Hypochlorous gases. That's free chlorine. That's what the efficacy of antimicrobials come from. If you keep doing the pH increase, at this moment, the dominant will be chlorine ions, chloride ions. I don't like that. We don't like that because there's not much antimicrobial efficacy. And this is a pH which is actually the correct without justified pH. So what do we do? How we justify pH? There are basically two ways to do. The industry person, they increase add citric acids. The second method is do the bubbling of carbon dioxide. The carbonic acid is going to generate, also going to lower down the pH. Okay, so that's very interesting to talk about chlorine. So using the chlorine is very tricky. In the conclusion, the container or the utensil to hold all the chlorine has to be clean as possible, because the organic matter will decrease the chlorine concentration, especially hypochlorous acids, very rapidly, very much rapidly. And the second thing is important is the pH justification. If you don't justify pH, at this moment, not much hypochlorous gas is going to generate. It's not very not very effective to kill bacteria. Okay, so this is important. Couple of years ago, there is a survey did for this online reprocessing of inside-outside birds wash for the chemical intervention survey. Originally, about like 20 years ago, chlorine is number 1. But 10 years ago, the survey tells us pre-acidic acids is number 1, followed by chlorine, followed by weak acid and ASC, acidified sodium chloride, CPC, EO, and bromine. So why? The reason is very simple. By the time people want to do the commercial business with European countries, especially with Russia, even Russia, they not allow you to process using chlorine. That's why they have to do hypochlorous gases, which is peroxyacetic acid. That's why periacidic acid is number one. So, what is perioxyacetic acids? Perioxyacetic acids is a reaction between acetic acids. This is acetic acid with hydrogen peroxide, H2O2, and then become CH3, CO, carbonyl group, and OH. This is perioxyacetic acids. And this product is very effective. They could be up to use 96 parts per million during the poultry meat processing. It is organic certified. In organic processing, you can use perioxyacetic acids. However, it is a little bit expensive, and what's a bad thing? It is very corrosive because it's an oxidization. How you can see it? If by occasionally there are some of drops of the perioxyacetic acids on your pants, it's going to happen to decollate, very obviously. Now these days, they have a perioxyacetic acids combined with hydrogen peroxide. They generate a new product called Sanidate 5.0. This is a new product which is recommended by West Virginia Small Farm Conference Center in the region they're going to use it. It's a new product. Okay? So this is what the hydrogen perioxyacetic acids looks like. So chlorine I already said. Now weak acid, I want to give you some of the example. What's a weak acid? Weak acid could be acetic acids. That's what we just talked about. It could be benzoic acids. That's benzoic acids. It could be citric acid. Remember we talked about citric acid? It could be citric acid. CH2, COH, COOH, CH2, COOH, could be citric acid. Now those we call it a weak acid. What happened? The weak acids, they all have, all COOH will have two separate expressions. This is we call it a free available ions, and this is we call it an undissociated part. And this part we call it a dissociated part. And we have to care about this guy is that pKa value, because at the pKa value, the concentration of them are the same. Is that right? Now, when we will talk about your killing bacteria, they have to be penetrated into the bacterial cell membrane system. When they penetrate the inside, only this all COOH gonna come in, which means our dissociated section will be going to the bacterial cell wall. So let's give you a bacterial cell wall. Cell membrane system like this, for example. So when this happens, what is going to happen? They will more or less will be dissociated something. So when they come in, this comes. So what is the proton for here? That's acid. Is that right? Bacteria cannot survive in the acid environment. What they have to do? They need pumping these out. These need to be pumping out. At the same time, they rely on ATP reduced to, hydrolyzed ATP become ADP and PI, and this is need ATPase. So bacteria keep pumping proton outside of the cell membrane, which means they'll keep using ATP. What this means? You're going to exhaust them during the metabolic process. Is that right? So that's a procedure. Why those weak acids could kill bacteria? However, it doesn't work really well lots of the time because there is a modification pathway bacteria could control by themselves. They become what? Acid-resistant bacteria. And acid-resistant bacteria could generate the cross protection by themselves, even if exposed to the future heat treatments. So this is something I want to talk about is weak acids. ACS, acidified sodium chloride, this is the one people generate recently. It's just the chlorine water at a low pH. So not many people use it because all gas going to come out. Next one is CPC. CPC, this is a cerium chloride. Cerium chloride, I did it one time during my research, and it's very effective to kill bacteria. Do you know what is this guy? What is CPC really for? Mouth washer. Some of the products are mouth washer, you see the bubble comes out? That's CPC. So, once upon a time, they used during the inside-outside both wash processing, but not too many. We want to talk about this guy. EO. What is this? Electrolyzed water. I tell you what, this guy is very interesting. Electrolyzed water is very interesting. The European country did a lot. There's a big chamber. We're going to have to charge them. Positive and negative. This is called anode. This is called cathode. And of course, this is water. Okay? H2O. What they're going to keep dumping? They're going to keep dumping is sodium chloride. Of course, the sodium chloride has to be food grade. Okay, not chemical grade. Okay, then what happened? Water is very stable. There is only one scenario they will break down. Is the electron. Is that right? Become this. There's only one thing they're going to break down. So, this OH will go here. Okay, somewhere here. Okay, H will be somewhere here. OH will be here. OH here. Everywhere. What are this guy? This guy will have CHO here and Na sodium fluid. So what happened? In anode, they will generate this guy. Here will generate sodium hydroxide. What is this? Free chlorine. This is. And what is that? Cleaner. So, electrolyzed water will generate sanitizer on the positively charged anode and the cleaner, which is sodium hydroxide from cathinode. It's a very good combination. One is a cleaner, another one is a sanitizer. So once they generate these products, they use it in the food processing, but not many people use it because this machine is expensive by the time. The commercial product part is trustworthy. And that machine somehow like $70,000, a big one. Cheaper, like $5,000. Another thing I want to tell you is at the beginning, this is really acid. So we call it acid electrolyzed water. Later on, they did something for this membrane system. They could come back with each other and neutralize. So becoming neutralized electrolyzed water. But the bottom line here, the key, is this hypochlorous gases. That's a free available chlorine. Okay, so that's what is for electrolyzed water. Very interesting stuff, but not many people do that. So this is inside outside the birds wash the chemicals they're using. Okay, chilling processing. prop chilling is very important. It could be very effective to kill bacteria. And we call it a multiple hurdle process. Why? We add chemicals there. We add antimicrobials there. And also the exposed time is important. The chilling time, we have enough immersion time, at least 45 minutes to 6 hours even. Sometimes 1 hour, 3 hours, 6 hours. You have chemicals there, you have antimicrobials there in the chilling tank, and you're dipping the birds there, the exposure time is well enough. At least 45 minutes. There's enough time to let the bacteria expose to the antimicrobials, so it is the most effective way to killing bacteria. But there's something we say, you need to do it effectively. Now in the United States, the same as inside-outside birds wash, peroxyacetic acid is #1, followed by chlorine, and the other chemicals using very little. The same thing, they want to sell the products to European countries and to Russia especially. They allow you to have peroxyacetic acids. You cannot use chlorine-produced products, treated products. Now, the chiller is important. We have to make sure the organic load is lower. So one of the factors will be impact organic loads, bleeding out, no bleed left. No fecal samples on the skin surfaces. Make sure the scottering is countercurrent. The water flow is countercurrent. And I said very importantly in a couple of slides before, the scottering temperature control is very important. If it's too high, you'll release fatty acids. Now, of course, number of carcasses rings. How many carcasses you're going to put onto the chiller is important. The more you added, the more organic matter will be there. How many of the birds you did inside outside the birds watch previously, that could reduce organic load and the flow rate direction in the chiller. Better also you do is countercurrent. And this is something I want to tell you. That's what I just said. The scottering temperature is important. This is what happens if your scottering temperature is doing more than 64 degrees Celsius. The fat will be generated from the skin surfaces and floated in the chilling tank. Look at how bad it is. You cannot even see the water there. Now what happened? If your incoming birds is 40% positive for salmonella, after chilling, the outcome birds is 53% positive for salmonella, which is not decreased, which is actually increased the cross-contamination rate of salmonella. And these are the huge organic matter will be dramatically affects free chlorine concentration. So if you have 50 parts per million, I would say 25 seconds is bring down to 0 and not going to kill bacteria at all. That's why the cross-contamination rate is dramatically increased. So that's why the temperature control is important. Luckily, we have some good examples. This water birds, the birds chilling water is really nice. But unfortunately, this doesn't take a picture in the United States. This is in El Salvador. This is another good one. Look at the water, very clean. This takes a picture in Chile, in South America. It doesn't come from the United States. Because it's hard to find a really very clean water example in the United States in those plants. But surprisingly, our positive rate looks fine. We'll talk about that. Okay, what the EU do? Air chilling. European Union countries, they do air chilling. They have the birds there, they blow with cold air, like 40 degrees Fahrenheit, 4 degrees Celsius. And no antimicrobials, you can do it. Now, a long time ago, people were trying to use chlorine dioxide. However, it's a gas and difficult to control the concentration. There happen, there's outbreaks for the human being, so they start to use that at all. So European countries, they use air chilling. Very important. The positive rate of broil in the United States is very much controlled. It's well below 5%. EU is about 15%. Australia is as high as more than 35%. So very lucky to see our birds are safe. And we have to say something. Why our birds is relatively lower percentage of salmonella? Because we do in-house processing control. We have chemicals. We have antimicrobials. In the EU country, what they do, they usually do not use really antimicrobials. They do the pre-harvest control, which is using vaccination, for example. And they're using competitive exclusion, which means they're feeding lactic acid bacteria. But they do not do much of the in-house processing control. That's why their percentage is higher. Another reason is that the EU country is more diversified. So you may find that the birds salmonella positive in Netherlands is only 1%. In Germany is only 2%. However, you can go to Poland and Hungary, you may see 30%. So when you do the average, it's somewhere between that. So that's why the rate is relatively high, okay? Campylobacter is the same thing. This is the survey did in 2015. The post-chilled broiled carcasses of Campylobacter positive is about 10% in the United States. European Union and Australian, very high, somehow like 7 to 80%. The reason is that Campylobacter is difficult to control. There is no vaccination for that. So we do need an in-house control for that, which means we do need antimicrobials in the chiller and inside, outside the bird's wash. Those are procedures which is important because you combine them together, we call it a multiple hurdle procedure. So luckily we see it's good. That's the reason, based on this survey, we set up our performance standards is 7.5 and 10%. So you can go back to see. That's one of the reasons. Campylobacter, you see the table, is about 10, salmonella is about 5, 6. So we set our performance standards is below 7.5 for salmonella and 10.4 for Campylobacter. Now, last thing I want to talk about, how about in West Virginia? What we do? We don't have a big poultry processing plant, we have a small producers. We do mobile poultry processing. There are two different types. This is a bigger one. Oh, sorry, this is a smaller one. Open air mobile poultry processing units, about $30,000. And now you can do 90 birds, 50 to 30 birds a batch. However, the waste control is important. It's difficult to do. But you can drive everywhere. And there is 2 units which is rented by Department of Agriculture and the Farmers Market Association in Charleston. And they are trying to rent these for the local small producers. We also could do is a relatively expensive stuff, which is $90,000 enclosed MPPU. This usually can process 120 birds an hour, and the per batch is 200 birds. And these, you have to go in